everyone. In this video, you are going to put yourself in the place of a business person. So what we're studying right now is, given a set of constraints, how can you come up with an optimal solution? And an optimal solution might mean a few things. If you're a business person, the optimal, which means like the best, solution would be when you make the most profit and use the least amount of money and resources. Okay, so I like to think about this in a business context. It's not the only context, but it's good to think about. Okay, and this topic is called linear programming, which is, again, just looking at a set of constraints and figuring out an optimal solution. Okay, so for our problem today, ETHS is holding a 10K race, and they must hire workers for 1 day to prepare the packets. Student workers cost $40 per day, and skilled workers cost $60 per day. So you can see how that would be a constraint there. You don't have unlimited money, so you can't make unlimited packets because you have to pay your workers. There's only $1,440 in the budget to spend on the race. Okay, there needs to be at least one skilled worker for every 3 students, but at most 16 skilled workers are available. Again, you don't have an unlimited amount of workers. You only have so many people available. Like, all these things limit how much profit a company can make, or in this case, how many packets can be prepared. Skilled workers can prepare 25 packets per hour, and students can prepare 18 packets per hour. Find the number of each type of worker ETHS should hire to maximize the number of packets produced. And I should say, not that students are not skilled workers, but what this problem means is that people who are trained to prepare packets, or professionals, however you want to think about it. Okay, so what I want you to try right now is to think about this problem and just word problems in general, and to define your variables. Be as specific as possible, and I'll come back with the answer. Okay, so I've completed the first step. You always want to do this when approaching a linear programming problem, because the variables define not only what you're trying to find, but they also help you check your equations that you'll set up. Okay, so I said X is the number of student workers. It's important to say number because you're not talking about the age of the student workers. You're not talking about how much money they make. I mean, you have to be very specific, otherwise you won't know what your equations are calculating. Maybe this context it isn't as important, but other contexts it is. Okay, the next thing is we're going to write the constraints. Okay, so the constraints are the various factors that affect the amount of thing you can produce. So it's a factor that affects how much profit you can make, or it's a factor that affects how much product you can produce. In this case, the constraints are what affect how many packets can be made. So like resources are a constraint, money is a constraint, time is a constraint, whatever those things you have in a problem are what you're looking for. Okay, so I want you to try this. I want you to write equations that match your constraints, and as a hint, there should be 5 total. I'll come back with the answer. Okay, so a strategy for approaching writing an equation from a word problem is to highlight the important numbers and information you're given. So I try to color code them by common themes. So everything highlighted in yellow refers to the money constraint. So workers cost $40 and $60 per day, but we only have $1,440 in the budget. That all has to do with the constraint of not having unlimited money, but having to pay people. Okay, the next constraint has to do with restrictions you have to be the most successful. Like you have 1 skilled worker for every 3 students. So students need someone to oversee them. You need at least one of them. And I should even highlight that at least. That's important. But at most, you only have 16 skilled workers available. So unfortunately, you only have so many skilled workers that you can find. There's not an unlimited amount. The only thing I didn't highlight was this 25 packets per hour and 18 packets per hour, which I will talk about why once I get there. Okay, so for everything I highlighted that has a common theme, there should be an equation that goes with that theme. So the first theme is money. I only have $1,440. There should be a constraint that uses this and the other money equations. So if I take 40 times X, that'll tell me how much I have to spend on student workers. So $40 per student. 60Y is how much I'm spending on skilled workers. Okay, so this common theme is money here. Now, I've set that equal to $1,440 because I only have $1,440 in the budget. Okay, this is what I see people think most off the bat. However, if you're thinking in a business standpoint or context, we should start thinking that, okay, if I'm a business person, do I want to spend every dime in my budget? If I don't have to, the answer to that would be no. Okay, I definitely can't spend more than my budget because I don't have the money, but I could spend less and that would be okay, or I might spend less just because of what I decide to produce. So these constraints should all be written as inequalities. So this can't exceed 1,440, but it can be less. So 40x plus 60y is less than, or it can also be equal to 1,440. Okay, next one, it says skilled workers, or excuse me, it says at least one skilled worker for every 3 students. So I wrote my equation as y equals 1/3 x. You may also write this as 3y equals x. Okay, but again, this says at least one skilled worker for every 3 students. So that key word is saying, well, I need one for every 3, but I could have it more than that. I could have 2 skilled workers for every 3 students, at least one, and that's a key word you need to be looking for. So while I see a lot of people who use equalities for these, it needs to be an inequality. So my inequality is going to look like this. Now, I know some people sometimes get confused, like when am I putting the y, where am I putting the x for these problems? And this is what I recommend. 2 things. Always go back and interpret your equation. So what this says is the number of skilled workers, that's y, has to be greater than or equal to 1/3 of the amount of student workers, because you want to have more student workers than skilled workers. And if that doesn't make sense, then you can always plug in numbers. So say x is 3, then y would be 1, and you have more student workers than skilled workers. So that's the way I want it. You also want to double check the way you have your inequality facing. So what this says is the amount of skilled workers can be greater than or equal to 1/3 of the student workers, which is what I want, because I said we need to have at least one skilled worker for every 1/3, but I could also have more skilled workers. So always go back and read your equation in its context using what x and y are to make sure it makes sense. Okay, my last one I set up from the highlighted information is, it says at most 16 skilled workers are available. So at most means there are 16 workers that are available. I don't need all 16, but I definitely can't have more than 16. So it has something with y equals 16, but since it says at most, it means that y cannot be greater than 16. So y has to be less than or equal to 16. These are all inequalities. Okay, so that's all the information I highlighted, and then you're probably thinking, wait, you told me there should be 5. The reason there's 5 is because this is a real context, and x and y are real quantities of things. So a couple things to consider is that you can't have a fraction of a student worker. So I couldn't have like x equals 1.5 because you can't have a half a student. But also it can't be negative. I can't have a negative amount of skilled workers. So the last constraint we always need to include when we're setting up these constraints is that my variables in a real context have to be positive integers. So I can write that by saying y has to be greater than or equal to 0, and x has to be greater than or equal to 0, where x and y, and this is something you can just check at the end, x and y are integers. If you don't get integers, you'll have to round up or down depending on the problem. Okay, so now I have my 5 constraints. I can graph these inequalities, which we'll do in a second. But the last thing that you always want to get from this information is something called the objective function. And the objective function is just the equation, or function, I guess I should say, whenever I start writing equation, that calculates the optimal solution. Optimal meaning the best solution. Okay, so in this particular problem, our optimal solution will happen when we have the maximum number of packets produced by each type of ETHS worker. And that's where this last piece of information comes in handy. So to calculate how many packets are produced, students can produce 25 an hour, and, skilled workers can, and students can produce 18 an hour. So if I do 25 times y, that'll say, okay, if I have 3 skilled workers, they would produce 75 packets. So that last information is to help you calculate your optimal solution. So to calculate the objective function that will calculate the optimal solution, I would have the number of packets produced would be equal to 18x, so 18 packets per student per hour, plus 25y. Okay, now to actually get the optimal solution, I need to figure out what x and y are and how many workers I'm going to have in order to determine how many packets I can produce. And that's where graphing and systems solving comes into handy. So what I'm going to have you do is I'm going to have you graph these, and I'm going to pause the video and come back with the answer. But we can call this point 0, 0, because one of our constraints is that x and y have to be greater than or equal to 0. So it can only be in the first quadrant of our coordinate plane. So I've already graphed 2 of those constraints for you. Now what I want you to do is go ahead and figure out how to graph the other 3 constraints on here, just assuming each of these is 1 increment, and I will come back with the answer. Okay, so I have that graphed. I color-coded the equations. I did have to solve for y in one of them to be able to graph it, so that's the work there. The red equation is the 1/3 x, the blue equation is y is less than or equal to 16, and the green equation is that longer one here. Okay, but these are inequalities, so in order to determine the solution, I'm going to have to determine where they all work together and make sense together. So let me show you what I mean by that. The solution to y equals 16 is not just this line. The solution to y equals 16 is actually y is less than or equal to 16. So I need to decide when are the y values less than or equal to 16, which would be when the y values go down from that line. So if this is the line y equals 16, the solutions are anything under that line, which I'm going to use highlighters to show this, and we're going to see where they overlap to determine the solution. Okay, my next one says y is greater than or equal to 1/3. So if y values are greater than or equal to 1/3, well, that's this red line right here. I want all the y values to be greater than or equal to 1/3 x. 1/3 x is this line where the y value is going to be more than this line. So y values go up or down. So all the y values are going to be greater than this line, upwards of the line. So the y values are going up this way. So I'm going to shade above this line. And if you're ever unsure where to shade based on the reasoning I'm giving you, you can always plug in a point and see where it's true or false, which I can show you an example of class if you would like to do it that method, but this is what I'll usually do. So the last equation says the y values are less than or equal to negative 2/3 x plus 24, which is less than or equal to the line negative 2/3 x plus 24. So that line is right here. I want the y values to be less than that line. So here's the line. The y values are less. That means they go down from the line. So the y values are less below the line here. So that's where I'm going to shade below this green line here. And my solution is going to be, where do all of these sets of solutions intersect? So like, when my blue and my yellow intersected, they made green. But I want to find where all of my solutions overlap. And that's going to be this really dark shaded region where all my highlighters intersect. They don't intersect up here because there's no yellow or blue over there. They don't intersect down here because there's no pink over there. They all intersect in this region here. Okay, so this is called your feasible region. The feasible region is where all your solutions overlap. And this one is bounded by 1, 2, 3, 4 vertices. And I want you to find the vertices of that feasible region. You can do this by just looking at the graph and counting, but if they're fractions, you're going to have to do that by finding where the 2 lines intersect. So this vertex would be where this line and this line intersect, which you can solve algebraically using a system. So pause the video and do it with whatever method you choose. Okay, so these are my 4 vertices of the feasible region. I did it by counting, so just check your work with mine. Now the reason I need to know the vertices is because the vertices represent my x value and my y value. So this means x is 0 and y is 0. And in order to determine what my optimal solution is, I need to figure out which x value and y value will produce the most amount of packets. So I'm going to use these vertices and plug them into my objective function and see which one is going to produce the most packets. So which combination is the best? The reason you can just focus on these vertices is because they're the most extreme values of the feasible region. So like I wouldn't pick a value in here to plug in because I already know like this x and y combination is going to be greater, or at least this x value is going to be greater, or this y value is going to be greater, this x value is going to be greater. So they're the extremes. And we can talk about that a little bit more in class, but you're always going to plug in the vertices and see what your optimal solution is. So what I want you to do is I want you to plug in all 4 points to the objective function and figure out how many packets would be produced for those values. I'll come back with the answer. Okay, so I've taken all the extreme vertices, plugged them in to see what my number of packets would be. Hey, you might have had a guess at the beginning which one worked and which ones didn't, and that's awesome. But it turns out the 4th scenario with 24 students and 8 skilled workers is the best solution for those constraints. So that's how you would solve the equation. We can talk about this more in class, but I hope you learned how to find an optimal solution.